So far, we've been looking at the most basic programs with just a few lines of code. However, some of the more complex systems written in C++ require many thousands of lines of code, even when the programmers use loops and functions to make the code as compact as possible. A major system like Windows takes tens of millions of lines of code. Now, how's that possible? The idea of writing that many lines of code seems overwhelming, and it would be overwhelming if anyone tried to write it alone. That much code is well beyond what any one programmer is capable of really writing and understanding well. One of the main ways that people collaborate is to produce code through a library. Think of a physical library. It's filled with books, each of which have some unique stories, information, or ideas. If you have access to a library, you have access to all the ideas contained in those books. Well, in coding, we also have libraries, but it's even better. Code libraries contain extra functionality. They directly give us the ability to do things in our code that we wouldn't otherwise be able to do. If we want the ability to do something special like perform a mathematical computation, then we can use a library for mathematical operations. A physical library gives us access to the books it contains, but a code library gives us access to additional functionality. A code library doesn't just let us read more, it lets us do much more. We've already been using an example of a library. We've been pound including IOStream ever since our very first Hello World program. And that's a way of giving the rest of our code access to a special library. I/O means input-output, and what the IOStream does is it lets us print output to the screen and read in input that the user types on the keyboard. Now, if we did not have access to that library, well, we'd need to learn how the computer stores information that gets sent to the screen, and how the individual keystrokes come in, and how we can use those really basic operations to do things like write text to the screen or read in a large number that's typed in. Now, with enough time and effort, we could learn to do that too. But someone already did all of that on our behalf by creating the library, so we don't have to mess with those details ourselves. There are a few good reasons to use libraries in our coding. First, they let us separate ideas in our code. As we develop more and more code, we're going to see separation of ideas as a recurring theme. Separating out different ideas lets us have a conceptually simple way of thinking about any one piece of code. And that kind of separation of ideas is critical to making large programs. In our input-output example, when we write Hello World, we don't want to have to think about all the low-level details of getting letters from the computer to the screen. We want to just tell the computer to output that text. And likewise, for the people writing the IOStream library, they didn't want to worry about each specific use of the library, like the particular text someone would want to write. They just wrote a general library for people to use as they want. Now, besides separation of ideas, a second good reason for libraries is reusability. We've often heard the phrase, "let's not reinvent the wheel." Well, the same is true for libraries. When someone has figured out how to do some particular task, there's no sense in us doing the exact same thing ourselves. Well, occasionally we might want to reinvent the wheel if we just want to learn the details of how a wheel works, or we think we can make a better wheel. But for the most part, we don't want to repeat unnecessary work. To see how libraries work, let's look at how code in libraries are actually compiled in C++. A library typically consists of two parts, a header file and an implementation file. Now you can think of the header file as the interface for the library. The header file basically makes a few definitions and declarations and says, here is what will be in the library, and here's how it can be accessed. But it doesn't necessarily contain the details of how the things in the library are actually implemented. When people write their own header files, the header file will typically have an extension that is .h. The H indicates that it's a header file. You might also see the extension .hpp, where the pp is added to show that the header is part of C++. Anyway, for standard headers, which we'll see in this lecture, we don't worry about any extension since it's automatically implied. We just write IOStream, not IOStream.h. Now the actual details of how the library is implemented are contained in a separate file, the implementation file. And this file will contain regular C++ code, and it will have a .cpp extension. If the file is just standard C code, it might have a .c extension. The implementation file has all of the details of how the things declared in the header file should be implemented. the implementation file will usually #include the header file at the beginning. So, as an example, the header file might define how a function to compute the area of a square should be called, what its name is, what parameters it takes, and what type it returns. The implementation file will actually implement the code needed to do that square area computation. Now, note that a library does not actually contain main function like we saw before. The library is not going to contain code that is run as the main program by itself. It's just going to contain functions that can be used by the main program. The library can then be compiled into what's called an object file. The object file is machine instructions, but these machine instructions can't be run on their own. Since no main function was defined in the library, it doesn't have any commands that just get executed on their own. Instead, these are machine instructions waiting to be used by some other program. Next, we have our program, the one that we want to actually make use of the library in. This is where we'll define main. It needs to know what functionality is available and how to use it. So to get access to that library's functionality, it will #include the library's header file. Our main program gets compiled into its own object file. But notice what's missing. This new object file does not have the actual implementation of the stuff in the library. Those commands are in the other object file, the library's object file. So, after all the compilation is done, there's one more step. That's called the linker. A linker will combine the main program's object file with the library's object file to create an executable file. The executable file now has all the information from both the program file and the library file, and it can thus be run on its own. Since a program is not too useful until it's linked with the library, the linking phase is usually combined with the compiling phase. In fact, when we talk about compiling, we usually really mean compile and link. The libraries are usually already compiled, well in advance. The standard C++ libraries are already installed automatically when you install a C++ compiler. If you ever create your own library, you'll compile that part ahead of time also. Also, realize that a program can, and often does, link with more than one library. The process is the same. There are just more header files to #include. Now, the first libraries to be aware of are a standard set of files that are included with every C++ installation. These libraries are collectively often called the C++ Standard Library, and there are about 50 of them in all. One we've already been using is IOStream, and in future lessons we'll encounter about 15 to 20 more of these. We'll end up using ones like vector, string, fstream, and algorithm. And these standard libraries are the ones to rely on first when you have something that you want to do. You just write a #include statement near the top of your program, putting the library name inside the angle brackets. Let's start out by looking at a couple of the C++ libraries that have been inherited from C. As you remember, C++ basically grew out of C. And C was, and still is, used for several applications, so there were a lot of libraries developed for C, including some standard C libraries. There's one for math and time and several others. Well, C++ still provides access to all of these libraries, where the name of each of them is C something. So the something will be the name of the old C library. Look at this code. In this case, we're going to use the CMath library. To do this, we'll #include CMath. Do you remember what #include does? It will take the header file, CMath, and put all that header file information into our code. One of the things that CMath will give us access to is a square root function, sqrt, which we can use in our program. In this case, we print out the square root of 2, which is 1.41421. Now, this is the first time we've really used a function in our code. We're going to be using functions a lot, both pre-built ones that we get from libraries, and later in this course, ones that we'll create ourselves. So let's take a second to see what they look like when we use them. When we use a function, there are two key parts. There's a function name, and then parentheses that come right after it. In the square root example, we have a function for computing square root, and the name is sqrt. After the function name, there will always be a pair of parentheses. Inside of those parentheses, there will often, but not always, be arguments. The arguments are values that we'll be giving to the function. In the case of computing a square root, we need a single number to take the square root of. So we need to have one argument, the number to take the square root of. When we write code and we want a function to happen, we write the function name and parentheses along with any arguments that we need to give it. And this is referred to as a function call. And we say that we're calling or invoking the function. It means that when we get to that part of the code, we execute the code corresponding to that function. Now remember, not every function needs arguments. Some will perform operations without requiring arguments, but they'll still have parentheses regardless. If the function is designed to compute some value, that function call is replaced by the value it computes. We say that the function has returned a value. For the square root function, we'll have a floating point value, the value of the square root, returned. And whenever we encounter a function call, if there's a return value, we can think of the function call as just being replaced by the value of that function. Again, back to our square root function call, notice that it occurs in the middle of an output statement. The value that is returned from the function is what is output. Now, the square root function, like all functions, is not defined in C++ all by itself. To have access to it, we needed to get it from the CMath library. The CMath library includes a variety of math functions beyond just square root. For example, CMath includes a power function, allowing us to compute one value to the power of another. In this case, the function name is pow, P-O-W. Notice that pow takes two arguments, the number that we want to raise to a power, and then the power that it's raised to. We separate these two arguments using commas. When we make the function call, it will return a value. So, since 2 to the third power, that is 2 times 2 times 2, is 8, it will return the value 8. And sure enough, when we output the result of the function call, we see that number, 8. The CMath library has a lot of useful math functions. Besides square root and power, it includes trigonometric functions like sine, cosine, and tangent, exponential and logarithmic functions, and many others that you might find on a scientific calculator, along with a few like gamma functions that you might not. The standard libraries provide a lot of useful functionality for us to make use of. There are dozens of functions located in the math library that we've looked at so far. So, I want to show you how to find out for yourself what they contain. After all, we don't always know what we don't know. The website I recommend is cplus.com, and it's a particularly useful one. I think it gives clear explanations for a lot of functions, including the standard C++ library headers. Try following the reference link on the site to find more about a specific topic. For example, to find information about the CMath library, follow the reference link and then search for CMath. That will show you a list of all the functions provided in the CMath library. Or just try a search engine. The first or second item in the search results may take you to the same location. Let's go through the process of developing another program, making use of another library function. We'll develop a small guessing game, where the computer picks a number and the user has to try to guess the number picked. To do this, we're going to need a function that lets us get a random number. Now, random number generation is actually a really tricky problem, and it's a topic that's been studied for a long time. It's nearly impossible to generate truly random numbers with a deterministic computer, but that's a subject for another course. The key is, we do have ways of generating what are known as pseudo-random numbers. They really seem like random numbers and are just as useful for most applications. Now, unfortunately, the method for generating these numbers is kind of complicated, and we don't want to have to learn all about pseudo-random number generation just to create a little game. Now, fortunately, we can turn to libraries where other people who do understand pseudo-random number generation have implemented ways of getting these numbers for us. A web search for something like C++ random can be the quickest way to identify a relevant library function from the standard C++ library, if one exists. Now, in this case, C++ actually has two standard libraries that will generate random numbers. One of them is called random, and it provides ways to use different algorithms to generate random numbers and create different random number distributions. but it's rather complicated to use, and there's an easier to use library that provides a good illustration for how we can make use of library functions. We'll use the C standard library, that is, cstdlib, to generate our random numbers. C standard lib includes the function rand, and it's widely used. Rand is a function that does not take any arguments, and it returns an integer. The integer will be some number between 0 and the maximum possible random integer. Let's look at a little bit of code that'll generate a random number. We have a simple program that we begin by pound including the cstdlib header. Then, we can use the function rand with no arguments in the code. This gives us an integer. If we run the code, we'll see that there's a random number generated. We can generate more random numbers by calling the rand function multiple times. Every time we call rand, we get a new random integer. In this version of the code, we have 3 random numbers generated. Now, there's something that might seem really weird. Try this out on your own computer if you can. Write the program and see what's output. Then run it again. And again. Now, you might get a different set of random numbers than I did, but you should find that every time you run the program, you get the same sequence of random numbers. That doesn't seem very random, does it? So what's going on here? Well, the way pseudo-random number generation works is that we have to initialize the numbers with a seed value. The seed can be any number, and the numbers produced seem very random. You can't tell that they're at all related to the seed. However, if you start with the same seed, you'll always get the same sequence of random numbers every time you call rand. Now, we can adjust this by setting the seed, which is done with a function called srand. Srand takes in one argument, which is the seed value to be used. And after calling srand, every call to rand will be generated based on that seed value. If you give the same seed, you'll get the same sequence of pseudo-random numbers. Here's what the code will look like with a different seed value. In this case, the seed used is 3. Now, if you run the code with different seeds, you'll get different sequences of numbers. Try this out. Put in different seeds, and you should get a different set of numbers. Here, if we use a seed of 3, we get numbers like 1.2 billion something, 483 million something, and so on. And if we instead use a seed of 4, we get 1.968 billion, 287 million, and so on. Notice that the sequence you get for a seed of 3 is very different from that for a seed of 4, which would be very different from a seed of 5, and so on. If we want something that seems even more random, we can try to choose a seed without having to specify a number. And a common way of doing that is to use the current time as the seed value. So, even though the numbers are not truly random, no one is going to be able to guess the actual digits ahead of time. Now, how do you think we can get the current time in our program? Well, there's a library called ctime that will give us the time. Look at this code. We've pound included the ctime library. That gives us access to a function, time, that will give us a current time. The time function takes one argument, which we should just set to 0. Don't worry about the details of this argument, that's not important. The key thing is that the function time will then give us a different value at every time, based on the current clock time. Now, if you run this code, you'll get a different sequence of numbers every time you run it. Since the actual time in the computer is changing every second, the time function is giving us a different value all the time. And so every time we run the program, we have a different seed. So, now that we're able to generate random numbers, let's say that we want to limit our integers to a more limited range, like 1 to 100. One way to do this is to use the modulus operator. Remember that the modulus operator gives us the remainder after dividing. So, if we take a number, mod 100, then we get the remainder, which will be something between 0 and 99. If we had random numbers to begin with, then we'll still have random numbers afterward. Then, if we want a random number to be from 1 to 100 instead of 0 to 99, we just add 1 onto the modulus computation. So, let's look at a modification of our previous code that will generate random numbers in the 1 to 100 range. We've now changed it from just plain rand to be rand modulo 100 plus 1. If we run this several times, we'll see that we get random numbers, all in the range of 1 to 100. So, say we want to make our guessing game. We'll want to pick a random number and then repeatedly ask a user to pick a value, telling the user if they're too high or too low. We'll see how long it takes for the user to guess the right answer. Let's work through the code development together. Remember that we want to start by writing some pseudocode, giving an outline of what we want the program to do. Can you think of what the major steps in this program would be? Okay, here are the steps that we want to go through. We first generate a random number. Then we get an initial guess from the user. And we'll repeat as long as the user hasn't guessed the number. Each time we'll report if the last guess was too high or too low. And then the user gets another guess. And at the end, we output the result. The next thing to do is to use the pseudocode outline and convert it to comments in the code. We take each of the steps and make them a comment within main. Now, notice that I've also gone ahead and pound included both cstandardlib and ctime, since I know we're going to be generating random numbers. Next, we want to fill in the parts of the program one by one. See if you can do the first one, based on how we talked about generating a random number. In this case, assume it's a number from 1 to 100. Here's the code. We set the seed using a random time, just like before. Then, to generate the number, we use the rand function. And as before, we take the result of rand, modulo 100, and we add 1. This all gets assigned to an integer variable, num to guess. Now, ideally, we should test the code at this point to make sure it's working, and then we'll gradually go ahead and fill the remaining steps in one by one. For the sake of time, I'm going to skip testing and move on to the next section. What would the code be like to get a user's initial guess? Well, getting a user's guess is just outputting an instruction with cout and reading in a variable, user guess, using cin. Since we want to keep track of the number of guesses, we create a numGuesses variable. Since this is our first guess, we initialize numGuesses to 1. Okay, how about the next comment line, setting up a repetition until the user guesses the right value? Well, this will be a while loop. We want it to continue looping until the user's guess matches the number to guess. So, the conditional is just user guess not equal to num to guess. Okay, on to the next segment. How would we report if the number is too high or too low? Here, we need a conditional. If the user's guess is lower than the number to guess, we report that the guess was low. Otherwise, we report that it was too high. We're nearly done. How would we write code for the next block, getting another guess? Again, we just print a message to the user to enter a new guess. Then we read that into our user guess. We also have to increment the number of guesses that the user has made. All right, for the final section, we need to print the tries. What would that code look like? We just have one output line where we output a statement stating the num guesses used. And that's it. If we run this program, we'll be able to play a different game every time. Now, let me encourage you to go back over that program and review it twice. First, do it with everything visible. See if you're able to follow each of the statements used and the commands that we used along the way. Importing the new libraries we need, cstandardlib and ctime, the srand function, the time function, and the rand function, the while loop, the if conditional, the input, and the output. Now second, run through it again, but this time see if you can generate something similar to the code all by yourself, starting just from the pseudocode. Remember how we generated a random number? We first need to import the cstandardlib library. Then, down in main, we started with the srand function with a starting seed. Then we generated a random number using rand. The program may take you a while to generate on your own, but if you work from the pseudocode, you can fill in each of the main steps one by one. You have all the tools you need. It's just a matter of putting them together. Here's the code again. The key things to remember are that you can import libraries, in this case for random numbers and for time, to get your new functionality. And you can use the pseudocode to fill in the program gradually. Now, remember that when we have #includes at the beginning of our file, we're substituting the contents of one file, a header file, into the program itself. You've seen that the library that we've been including is put into brackets, formed by the less than and greater than signs. Well, an alternative to using those brackets is to use quotation marks. If you look at this version of some of our earlier code, you'll see that I've replaced the brackets by quotation marks. The code works exactly the same in this case. Now generally, the convention is to use brackets for things that are in the standard library, and you use quotation marks for other libraries or files that you're including. This could be a non-standard library or a file that you've created on your own. The details of how the preprocessor handles brackets versus quotation marks is not a standard. Different preprocessors can handle them differently. But if you follow the convention, brackets for standard library headers, quotation marks for other things, you'll probably be in good shape. There are more libraries out there than just the standard libraries. People have created C++ libraries to do all sorts of things, from display 3D graphics to perform advanced scientific computation. Some of these can be easy for a novice programmer to use, and others are only suitable for experts in the area. If you're interested in finding additional libraries beyond the C++ standard libraries, one particularly good source is boost.org. The Boost libraries have all been reviewed, and a lot of what's provided there is very high quality. For example, the File System library provides ways of working with directories or folders and files on your system. Boost's Math library provides more advanced mathematical functions than are in the CMath library, like dealing with polynomials and complex numbers. In fact, some of what started out as Boost libraries have now been incorporated into the standard C++ library. Now, if you do some web searches, you'll run across all sorts of other C++ libraries out there. However, I would advise caution. First, every library has its own set of commands, and often just understanding how to use a single library, like a graphics library, could be a course on its own. Moreover, not all libraries that you'll find on the web will have been widely tested and verified, and it can be difficult to install and use some of them. You'll probably need to understand your system's file structure pretty well to do so. In short, it's often better to stick to more established C++ libraries, like the standard libraries, at least at first. Now, the use of libraries is critical to taking your C++ coding to the next level, to being able to make use of the tools that others have created to build your own code. You'll start out much better by building off of the good work of others rather than doing everything on your own from scratch. Fortunately, the #include process makes it easy to incorporate other libraries, particularly the standard library, into your code. As we go forward, we'll be using more of the standard libraries. We'll also see how the breakdown between header and implementation can be used when we get to object-oriented programming. In fact, over the next 2 lessons, we'll be learning about how to store large amounts of data in programs, and we'll do this first using arrays, and then using another of the standard libraries, a library called vector. Be there, or be aware, that you'll be missing a lot.